you see we dissolve different butters and also acetone to find out, to get the absorption weight and pressure. And since we have a similar curve to the beta carotene acetone for both, this is the target brand, this is the organic grass-fed butter, that peak absorbs in the same place and the curve is similar. So that helps us see that the beta carotene is what's doing the absorbance given the color. So here is, for contrast, is the goat butter here. So not only does the curve look quite nothing like the other two, but also that's very low absorbance. That's where you have to use dots instead of the line here. That's the low precision. So from this we can tell, we can infer that beta carotene is what's doing the absorbance in the generic and the grass-fed butter, but not the goat butter. Okay. And then finally, I made a solution of beta carotene and acetone, and then diluted different concentrations to the absorbance. So that way you'll be able to get a slope that would tell me, see, if you remember the original equation, absorbance equals TCC coefficient times half length times the concentration. So the slope of the absorbance versus concentration is going to give me this, which is going to be constant for the given compound in solution with similar settings, circumstances, same temperature, same pressure, yeah. So with that, we would see more concentration of beta carotene in the solution because one absorbance. And that's what we got here. These are from the data I took that you saw in the graphs before, the absorbance wavelength curves. And at the peak absorbance, about 470 nanometers, you got the Kerrygold organic butter's max absorbance was 0.17, and the generic was 0.19. That tells us, yeah, it's kind of speaks for itself a bit. But so with that, you go back one slide. This is what I want to see. So there's about roughly 3 times as much beta carotene in the organic butter than there is in the generic butter results. So with that, so now coming back to the results from last semester, and what they did, one of the first tests they did to try and find out the fatty acid content of each butter is to titrate it with bromine water. And something they observed is that as soon as about 1 milliliter into the titration, the color of the butter completely went away. And hopefully with this, we'll be able to see the change of color kind of infers a reaction to something happening with beta carotene and bromine. So now we know how much beta carotene is needed in our solution, where we kind of compensate for that and get a better idea from the titration exactly how much fatty acid content is in, or fat content is in each butter solution. Okay. Right. And I guess if you know, now that we know how much beta carotene each one has to know which one has more beta carotene. So even though it's not much, you saw it was on like a fraction of a percent. It would be healthier by eating organic dairy products, at least probably by that's it for me.
Okay, I'm Victoria. I'm going to talk to you about transesterification. So this is a process we use to separate. Well, so first what we do is we take the butter and we melt it, right? And then you get a fat layer, and a water layer. So we extract the water layer because we don't want that. And what you're left with is this fat layer. And what we want to do with it is then from the fat layer extract the fatty acids. So I don't know if it's had biology, but or chemistry, but fatty acids come in like a 3-to-1 ratio, right? So you have 3 fatty acids to 1 glycerol. So we use this process to separate the fatty acid. We use methanol as our reactant, and we use sodium hydroxide, which is a solid, as our catalyst. And if sometimes, like when you extract the fat layer from the water layer, there might be some water left, and that's not good because then you might make soap. So here's just the formula for the transesterification, and this is what we want it to look like. So this shows good separation. We have our methanol and our sodium hydroxide, and it gives us all our fatty acids, right? And there's our pretty methyl esters. And this is what happens whenever you still have water inside your fat and you get soaked, which is really upsetting because then it failed. And it's hard to get all the water out. And the reason we do this is so we can analyze it by gas chromatography, which Nikki's going to talk to you about.
So the gas chromatograph we used was, we have two, George and Sally. We actually installed a 30-meter capillary column, which is a lot thinner than a pack column, into George. So we used him to try to get better separation of the fatty acid methyl esters that Stanley and Andrew derived last semester. We developed a protocol using different compounds at first, and then we developed a protocol using the methyl esters, and we found that starting it at a slightly higher temperature at 70 degrees Celsius and ramping it at 3 degrees per minute until a really high temperature at 250 degrees Celsius, it gets better separation of all of the fatty acids. But when we ran the first, just the mixture by itself for the target brand butter and the Kerrygold butter, it ended up not being able to separate some of the fatty acids in the middle. There were some that had slightly, like very similar retention times, so their peaks were very close together and we couldn't separate them very well. So what we did was we tried to dilute the standard mixture that we actually bought, and with 10 drops of ethyl acetate, which will come off sooner, and the rest will come off later, and it actually caused a better separation. But what we need, the peaks that we needed, weren't well separated yet, so we tried with 30 drops, and that has actually given us some promising results because it separated one of the methyl esters that is supposed to be in butter, so we're still trying to get the unsaturated fat separated from that as well. So we're going to further dilute going forward. So basically the diluted mixtures gave us better separation. You can see here that this peak right here was not separated at first with the 10 drops, and now with the 30 drops it's completely separated. So we're able to say that that is methyl linoleate actually, which is actually one of the bigger components in butter that we're supposed to be able to find in butter. So what we're trying to do now is get this peak, which actually has our unsaturated fat, which is our methyl oleate. And it also has methyl stearate in it. So we're trying to get those two separated because they are also components of butter, and we're trying to figure out the numbers with that as well. So basically those are the so those are the methyl esters that are supposed to be in butter that we tried to separate. I did put that I need percentages in there because they're meant to be added. So far they're pretty similar, but the methyl oleate is what we still need, and hopefully we'll get better separation of that